All right, let's get started. So if you haven't turned in your quiz, now's the time to do so. I have the previous quiz and labs 4 and 3 here. So if you haven't picked those up, feel free to do so. Are there any questions? There's one thing I want to go over. So on the last quiz, quiz 7, pretty much everyone either got slightly wrong or totally wrong the second question. So it said that suppose L is regular and there, I'm just paraphrasing it, there is no string in the language with length at least p. And then the question is, what can we say about L? It's actually kind of it's not really in depth, but it's a really, really interesting answer. You can see that, right? Okay. Yeah, I can't really see it, so yeah. Okay, so we're supposing that there's no string in the language at least p in length. So let's see. Well, this says that there's no string in the language with length at least p. So what's the longest possible length a string could be in the language? If there's none at length at least p, well, what is the longest length of a string that could be in there?
Longest?
Yeah, the longest.
P plus 1?
P, although it doesn't really matter, but it's...
Well, it's greater than equal, right?
Yeah, I'm saying there's no string of like that. So you mean P... P minus 1. Yeah. So this implies all strings in L have length at most p minus 1. Okay? Mm-hmm.
Where is this? What L is regular?
So remember the pumping lemma statement that said that L is regular implies there's this constant p for L. I'm just paraphrasing the second question from the quiz. Yeah, but we're only looking at a regular language, and then supposing that there's that constant p, I'm just asking what happens if there's no string in the language of length at least p. So then we know that all strings in L have length at most p minus 1. Wait, so if every string has length at most p minus 1, what do you know about the language? How big could the language be? Yes, just finite. So that means that L is finite. Maybe empty, I don't know, but it's definitely finite for sure, because the longest length a string could ever be is just a finite number. But suppose there is a string of length at least p in the language. So now we're supposing there is a string in the language with length at least p. What can you tell about the language now? Well, let's see. So the pumping lemma says that for every string in the language with length at least p, there is a way to decompose it into 3 pieces such that we can get x, y to the I, z in L for all I. I'll actually just rewrite that instead of just hand waving it like a show. So now suppose exists. And this is actually a good idea because we're actually a little ahead in the lectures anyway, so we might as well just do this. Suppose there exists a W and L with length of W at least P. then the pumping lemma says that W equals X, Y, Z for some X, Y, Z, such that X, Y to the I, Z is in L for all I, at least 0. And also that the length of Y is at least 1. But that was just the second condition of the pumping lemma. Okay, well, yeah, so the pumping lemma says there is a way to put it into 3 pieces such that we can pump the middle piece, put as many copies of Y as we want into the string, and you always stay in the language. That's what the lemma says you can do. Well, notice something interesting. So let's compare X, Y, Z versus X, Y squared Z. So I want to look at the original string, or it doesn't really matter, but I'm looking at a string and the same thing, but I'm injecting another copy of Y into it. So I had 1 copy of Y before, now I have 2 copies of Y in there. What can you tell me about those 2 strings? Are they the same? No, how can you tell? They have different length. What if I compared, instead of X, Y, Z and X, Y squared Z, suppose I compared, use a different color, X, Y to the I, Z, X, Y to the J, Z, where I is not equal to J. So same question essentially, but I just have different numbers of Y's in there. What can you tell me about those 2 strings? They're all different. Yeah, they are different. So wait a second. So for every single choice of I, either 0, 1, 2, 3, 4, whatever, each one of them is a different string in the language. Every single one of them is different. So what can we tell about L now? Yeah, it's infinite. Because we just described a set of infinite strings that are in the language. XY to the 0z, XY to the 1z, XY squared z, XY to the third z, etc. because they're all different strings and each one's in the language. So this implies L is infinite. Yeah.
What if your DFA doesn't have any loops in it? Then how could you get a Y?
That's impossible.
You're right. Then it would just keep going.
Yeah. So this condition is basically saying that in the DFA, there's no string that you can accept that involves a loop somewhere. That's basically what the first one was, and the second one is there is one with a loop. Or not a loop, but a set of transitions that you end up at the same place. But yeah, same idea. So wait a second. So this actually tells us a necessary and sufficient condition for a language to be finite or infinite. So this actually tells us another interesting thing. If you have a DFA, you can test whether it has a finite or infinite language just by seeing, does it accept any string of length at least p? But you should be cautious in what I just said. So how many strings are there of length at least p? 8?
P.
Infinite of length at least p. So if I just said, well, test every string of length at least p, how long am I going to spend doing that? A heck of a long time, right? So is there a way that we can check that more efficiently? So this is actually a question that we're going to look at later in the semester, maybe like in a month or so. But it turns out you can. And the basic idea is you take the DFA for L, and then you intersect it with a DFA that just accepts the strings of length at least P. So it's just, you have a set of P plus 2 states, no, P plus 1 states, where it accepts every string of length at least P. You intersect the two DFAs together, and so that DFA will accept all strings in the language of length at least P. And then you just see, does the DFA accept anything? And it turns out you can answer that question. But any questions about that? So this is the main reason why I put this question in here, to make you think about when this occurs. So like, what can you say about L if there's no string in the language of length at least a certain number? Then it must be finite, for sure. But it turns out you can have an if and only if, and say if there is a string in the language of length at least P, then it must be infinite. So a regular language is finite if and only if there's no string in the language of length at least P. Any questions about that? Yeah.
Well, P comes from the number of states in the DFA, right?
Yeah. But for our purposes, all we care about is that it's just some number. Yeah. Okay. So I kind of wanted to switch gears a little bit and start talking about kind of a new topic, but it's still related to regular languages. And then that'll allow us to jump to the next set of material. So then you may think, well, for the language 0 to the n, 1 to the n that we talked about before, where n is at least 0. Oh, that's another thing. So some people on like the labs put like 0 to the n, 1 to the n like this as the language. So what is this language? Written like that, there's one string in the language, which is just a particular choice of n, some number of zeros, some number of ones. What you probably meant to say is that for every choice of n, this string is in there. Whereas this one, there's only one string in the language. And if you only have one string in a language, what is it? Finite, and then therefore regular. Whereas you probably meant this one, which is, what did we show about this guy? About 0 to the n, 1 to the n, where n is at least 0. Yeah, it's not regular. We showed that in class. Okay, so you may think, well, can a computer decide this language? And by that I mean, if I give you a string, could you figure out for yourself in principle that whether or not it has some number of zeros at the front, some number of ones at the end, and the numbers match? Could you do that with a computer? So like if I gave you the string 0, 0, 0, 0, 1, 1, 1, 1, could you figure out that the first half of the string is all zeros and the second half of the string is all ones? Yeah, in principle, yeah. So, do you have a question?
No, I was going to ask if it was like this kind of computer, or like just a normal
Yeah, like a normal computer, yeah. But it's impossible with a DFA, of course. So, what we're going to do is we're going to talk about a different model of computation that will allow us to generalize to solve this language, among others. So, what I want to talk about is, what are the things that we have done so far? So what are the models of computation that we've talked about so far, the main guys? Yeah, so the ones where we said we want to recognize a language. If I can spell language. Language, DFA, and NFA. basically the same type of model, although they vary a little bit, but they recognize a certain language. You feed a string in, and you land in a state that may or may not be accepting. And that'll tell you what the language is based off the strings that are accepted. What's another model of computation we talked about? Yeah, the regular expressions. So those are for describing a language. Because if I give you a DFA or NFA, you don't really have any idea in general what the strings that are accepted by that DFA or whatever. And with the regex, well, that is an efficient way to describe what the language actually is in a formal way. So we look at these models, and let's just say I give you a regex, like say 00 union 1 star 2 star. So, and I ask you to produce for me a string that thing that is within that regex's language. Or if I give you a DFA and I give you either the formal version of the DFA or a picture, and I ask you to start writing out strings that the DFA recognizes. Just start writing them out. So you could just say, okay, well, I'm going to expand the outer star and then apply the 2 if necessary, and then apply the inner star. But that's not really formal. So is there a way that we could actually generate the strings in a language using rules? So what I'm asking is, you could, in principle, just try the empty string and then try all the strings of length 1, all the strings of length 2, all the strings of length 3, and just see whether or not the regex could describe that string, or the DFA accepts the string, or whatever. But is there a formal way to actually say what the ways in which you can actually make the string? How can you actually make the string in a formal way? So we're going to be talking about these things which are called grammars. So grammars are a way of formalizing how do you actually generate strings in a language. So you start somewhere, you apply a certain set of rules, and then you end up with a string at the end. So right now we're going to talk about only grammars in a restricted context, namely the regular languages, but we will generalize them to the next topic after that. So therefore we need to talk about a regular grammar. And I'm not going to shorten it to RG or whatever, is a for tuple so the for tuple has V, we'll talk about each of these in a second. So V, sigma, so sigma is the one that we're all used to, the alphabet, R, and S. And I'll say which of these is which. So V is a finite, so everything of course is finite set of what are called variables. And I'll describe what a variable means and all this stuff. So sigma is a finite set of terminals. So if we have So terminals are basically the characters of the alphabet. But the literature has this being called terminals. Alphabet and terminals mean the same thing. So S, the fourth guy, is a variable, and it is called the start variable. So like with the DFA or NFA, there's a start state. Here there's a start variable. Same idea. And in fact, that analog is actually going to be really crucial later when we show that regular grammars have the same languages as the regular languages. So S, we're going to call the start variable, and R is a finite set of rules of the following forms. So the set of rules, I'm going to be restricting what the rules can actually be. Because I'm not talking about a grammar in the general sense, I'm talking about a regular grammar, which is very restricted. So there are actually 4 types of rules that could appear. And I promise I'll do an example in a bit. So the rules are always going to be of one of the following 4 forms. They could be a variable goes to empty. So this arrow means, well, actually I'll talk about that in a second. So that's the first type of rule. The second type of rule is a variable goes to a single character, where that character, of course, is a terminal. The third type of rule is a variable goes to another variable. Yeah, so a variable can go to another variable and nothing else. Or a variable can go to a single terminal, then a variable. So instead of having anything on the left side, anything on the right side, I'm restricting you in the rules to have a single variable on the left side, and either the empty string on the right, a single character on the right, a single variable on the right, or, in the order's important here, the terminal followed by the variable. So yeah, go ahead.
I was just about to ask about the order, actually. I'm assuming you'll probably go over why it has to be in that.
So the order technically isn't important. I could switch them around if I wanted to. I can't have both. So I can't have the terminal first and then another rule has it second, because that would actually change the model. But if I am consistent and only have it on the left or only on the right, it doesn't matter.
Okay, so the placement is arbitrary, but just so that it's consistent.
Right. So this is actually what is called a left regular grammar, because the terminal's on the left side. And then, of course, there's a right terminal grammar. Right regular grammar. Okay, so let's actually look at an example so that we can actually see what's happening here. So here's an example. So I'm going to have a start variable s. So s is the start variable. So s goes to empty. Actually, I'm not going to do that. S goes to a. S goes to variable a. A makes b s. A makes b. Actually, yeah, that's fine. Yeah, I'll leave it like that. So just a simple example. So what can you tell me are the variables in this grammar? Yeah.
S and A.
Yeah, S and A. So it's just the things that appear on the left side. So the variables are S and A. What can you tell me are the terminals in this grammar?
A and B.
Yeah, the lowercase a and b. Yep. Basically everything else. So you look at the variables, everything else is a terminal. And it's in the right form because each rule in here is one of those 4 forms. Okay, so let's just say that we want to generate the string BA. So we want to generate the string BA. So I'll walk you through it. So what you do is you always start at the start variable, of course. So then you start at the start variable, S. And then what I'm going to do here is I'm going to write a double arrow to mean I'm going to apply a rule. And here's what happens. What you're going to do is by applying the rule, the variable S right here gets replaced with whatever rule that you used. So for example, if I won't use this rule in this case, but let's just say I wanted to use this rule, S goes to A, then down here when I'm trying to generate this string BA, or whatever string, it doesn't matter, I replace the variable S with the right-hand side of the variable. So the capital S here is going to be replaced with A, with lowercase a. So in that case, I would generate little a. But can I apply a rule at this point? No, why? Yeah, it's a terminal and there's no variable there. If there was a variable there, then I could apply a rule because every rule has just a single variable on the left side. And we'll actually see that when we do BA. So let's actually do BA. So this was not possible. So let's try to do BA now. Well, should I apply S goes to empty or S goes to A if I wanted to make BA? No, because if I try either one, then we're gonna get stuck. So I can't get any more characters. So the only possibility is which rule?
S goes to variable A.
Yeah, S goes to variable A. So the variable S here gets replaced with the thing on the right side, which is just the variable A in this case. So variable A. And then now we have to apply a rule where A is on the left side. So which of the 2 rules for A do you want to try? Yeah, BS, because if I try to apply the last one, then the only string that we have is just little b, but that's not the whole thing. So we're going to replace the capital A with the right-hand side of the rule that we choose to apply, which is BS in this case. Okay? So the goal is to always have a string full of terminals, no variables at all. So if we have a variable left, we still got work to do. So the terminal here, B, that we just made, that'll never ever change because there's no rule where we're replacing the terminal B with something else. We're always replacing a variable with stuff. So let's see. Well, that variable S looks a little pesky to me. Which rule should I apply for that one if I want to obtain BA?
S goes to A.
S goes to A. So the B sticks around because it doesn't change. And we applied S goes to A, replace the S with the terminal A, and voila, we have a string full of terminals, the one that we wanted to make. Cool. Yeah?
Would you ever want to use S goes to like just to make everything?
Well, I'm not sure what the question is.
When would you want to use the first one, the S goes to?
Yeah. So when would we want to? The only reason in this grammar is if you're trying to make the empty string. So that's the only case in this particular grammar. But it'll turn out that having this a rule like this is actually very important because what you see here is the only way that. So actually, let's actually examine this. I know you have your hand up, but I'll get to you. So let's look at this. So at each step along the way, how many variables do we have, including the last one? How many variables exist at any one time? 1 or at the very end, 0. So the epsilon and the single terminal variables allow the one variable to disappear. So we start off with one variable, then we're carrying the variable around until the very last one, which either replaces it with a character or just drops the variable away. So that is actually really important in terms of showing that this is equivalent to, that the languages of these grammars is the regular languages, but we'll get to that in a bit. Yeah?
So I have a similar kind of question, but it's like the opposite. So with the one where it's the terminal, then the variable, we only have one, but, and maybe this isn't necessarily like important, but like, what if you wanted to guarantee that it was like B, C, like in that order and then a variable?
So like
you have multiple terminals and then the variable.
Yeah, so it turns out you can. So the question is, if we have something like, if we have A goes to 2 terminals and then a variable, so I can actually do a substitution for this. So I can replace this with 2 rules. What I can do is have a new variable D, and I'm going to have the first rule be A goes to BD, and D goes to CS.
This might be something.
Okay, so yeah, so you can shrink the right hand side the right hand side of the rule to have a single terminal or fewer. Yeah, because you can just replace it if it has more with a bunch of rules. It would be wrong to have a terminal on both sides. So, because that actually increases the power of the grammar, as we'll see probably next week. Yeah.
Wait, with this question, were you saying that the A to BCS is not possible, or it's just like you should do the two rules?
So it determines what you mean by possible. So can you write a grammar that has like that? Yes. Can you write a regular grammar like that? No. Because the regular grammar says that you can only have exactly one. But we're going to be increasing the power of these grammars next week that allow you to put anything on the right-hand side that you want. So you can have any number of terminals and variables. But here I'm restricting you to have one. And even if you wanted to change the model where you have more than one terminal on the left side of the variable here, what the question was, you can always just whittle it down to one terminal and then you recover the original definition. So it doesn't actually change the model. Yeah.
Can you go from one character to, one variable to the same variable, like in Rule 4?
Yeah. So by the definition of regular grammar, yeah, you could have a variable goes to itself, but it's not very helpful. Because like if you apply the rule, nothing changes. But you're allowed to have it if you want. Any other questions about that? So this sequence right here, where we start with the start variable and start applying rules to get a string, this is called a derivation. Oh, you can't see, sorry. I'll rewrite it. I wanted to make this like very colorful.
Sorry.
This is a derivation. I promise we'll get that projector fixed at some point. Okay. Yeah, so this sequence of rule applications is a derivation. So we say that if G is a regular grammar, then the language of G is the set of all strings in sigma star, where G has a derivation of W. So it's a similar idea to DFAs. DFA says it has an accepting computation on W. Here, it's just the grammar can make W. And crucially, W is a member of the terminals star, so it doesn't have any variables in it. So it's just a string of all terminals. Okay, any questions about that? Okay, so let's go back to that question or that point we were talking about earlier about there's either one variable that we kept around the whole way, or at the very end it drops out. So if we wanted to show that these are equivalent to regular languages, well, if I wanted to show that these were equivalent, what would we have to do? We would have to show that if you have a regular grammar, you can make a DFA or NFA or regex. And conversely, if we have a DFA, NFA, regex, we can make a regular grammar if we wanted to show that they're equivalent. So let's think about this. So you always have a single variable with you until the very end. So think of like how a DFA works. How many, or even an NFA, how many states are you in when you're computing a string with a DFA or an NFA? Just a single one. Do you think that's a coincidence here? So it turns out that we could, that's actually the right intuition here. Because you only have one variable with you until the very end, that is actually how we can show equivalence. So let's actually do that here. So regular grammars recognize exactly the regular languages. Okay, so we would need to show, of course, two directions. So we need to show regular grammar can make, it'll turn out that making an NFA is easier. So let's just make an NFA, but we showed before that it doesn't matter which one of the three that you pick. And we also need to show that from an NFA, we can make a regular grammar. Right, because if you want to show that two sets are the same, you have to show that, or one method, I guess, is to show that one is a subset of the other and vice versa. So the languages of regular grammars is a subset of the ones that are recognized by NFAs and the other way. And therefore, these two sets are equivalent. So what are we going to do here? So let's do this one first. Yeah. trying to think which one is the easier one. They're actually both easy, and they're almost, one is the opposite of the other one, like doing it in the other direction, but it's just that there's a very slight difference between them. So let's see. So if we have, let's just say that we're going to copy down our grammar. So I'm going to copy this down so that we can work with it. Okay, so remember, we always have one variable with us until the very end. So for that reason, let's just make a state machine, an NFA, DFA, whatever, it'll be an NFA, where each of the variables in the grammar is a state in the NFA. Well, we have two states right here. So in a different color, I'm going to have two states, S and A. So let's handle these two rules first, because these are the easy ones. So let's look at the S goes to A rule. So it says that if we're an S, we're not going to produce any characters in the derivation and immediately go to A. So in the NFA's perspective, what should we do? Yeah.
Epsilon transition to A.
Yeah, epsilon transition to A. Good. And then that A to BS rule, what do you think we're going to do on that one?
Have a transition on B.
We have a transition to S. Yep, have a transition on B. And so that's actually the reason why we only had one character allowed on the right-hand side with a terminal, with a variable, because if we had more, then I would have to put more than one character on these transitions. But by only having one, then I can make the transitions work. And what is the start variable in this grammar originally? It was S. So what do you think the start state is here?
S.
It was S. Yep. Good. But it, of course, it's just those pesky three other rules. Why are they pesky?
Because they're not going to a state.
They're not going to a state. Shoot. That seems kind of annoying, right? Well, let's think about it. Yeah, go ahead.
Oh, I was just gonna say maybe we would have like extra states that you could epsilon transition to, and then just use whatever character that is to go to some other state. That's a final state.
You stole my thunder. No, it's fine. So let's actually really think about it, though. So when we started out with the derivation, we only had one variable. We had one variable, one variable, one variable until the very end. And so once we get rid of that variable, could we ever apply another rule after that? So whatever happens in the machine, we must be able to go to a state where we can't do anything else. So we have to be able to go to the state, we have the string finally read and all done, and we can't go anywhere else. So, and for that reason, because we produced a string entirely full of terminals, that must be the state where we accept. So therefore, I'm going to make a brand new, maybe in a better color. Yeah, I'm going to make a brand new state QF, which is final. And then from S to this state, I'm going to put what the rules say to do. So S goes to QF on epsilon and A. And then the last rule says A goes to B, which means that the transition to QF now has a B on it. And QF has no transitions leaving it. So it's basically a way to stop the computation and just exit out of the thing. Whereas the other two states, we currently in the grammar have a variable still alive, and the remaining transitions allow us to eliminate that variable. Pretty cool. So what you do here is you make a state for every variable. You relate the variables to each other according to the rules in the grammar. And if it is one of the other two types of rules, you make a new state, which is final, and you go to that state accordingly. So whether it's an epsilon transition or a character transition, you go to that state. Any questions about that? So that shows that if you have a regular grammar, you can make an NFA. But now, of course, we need to show the other direction. If we have an NFA or whatever, we can convert it into a regular grammar. So let's actually do an example. It is almost as easy. I'm just making up a random NFA. So just a pretty simple 3-state NFA. So note something interesting. So this NFA is not like the NFA we just made, where the final state, there's only one. And actually, I'm going to make Q1 also final. Where the NFA we just made had only one final state and nothing leaving it, whereas here we don't have that anymore. So what do you think we could do if we want to produce a regular grammar from this NFA? Yeah.
Well, with like the final state thing, we could make the current final states not final and then have a new final state.
You could. There's actually an easier way to handle that. So what did we do before? We had the variables are going to be states in the NFA. What do you think we should do in this case? Have the states become variables in the grammar. So in the grammar, we're going to have variables Q0, Q1, Q2. And the terminals are just going to be the things on the transitions, which are A and B. So what are some of the rules here in this that we're going to make in this grammar then? Well, say that first transition from Q0. So Q0 is going to make A Q1 because we go from the variable Q0 to the variable Q1 and we want to produce an A because we're reading an A go into that state. What's another rule? I'm only going to do one more because I want you to be able to do the rest of them. What's another rule?
Yeah. Q1 goes to AQ2.
AQ2. Well, if we just do these, then it's going to be either terminal variable on the right side or just a variable on the right side because it's always from a state to another state. Well, if we just did that, well, the grammar is not going to produce anything because you're always going to have that variable still around. So that's where the final states come in. So the final states allow you to say, I'm done generating the string. So here, what we're going to do is for each final state, what should be on the right-hand side of it here?
Just the terminal?
Not the terminal, epsilon, because it allows us to stop the computation right there. So for each final state, we're going to do this. And if that seems a little rushed, I think we're out of time, but we can revisit this on Monday and talk about it more if it was a little fast today. So I'll see you on Monday. Have a good weekend.